This is a low note E. But if I pluck this string, I get an E note which is 2 octaves higher, despite the string being the same length. Weird. Hello and welcome to Underdog Physics. In a previous video I raced through some standing wave basics, but I appreciate now that I was trying to cover way too much in just a single video. I've decided to unpack the magic which is standing waves in a series of videos which are much more easily digestible. In today's video I want to discuss how string material and tension dictates the fundamental frequency that we get. First things first, when we pluck a guitar string we're actually hearing a combination of lots of standing waves that fit on that string simultaneously. The main one that we hear is the fundamental frequency. That's the lowest frequency, or the longest wavelength that'll fit on that string. The speed of a wave on a string is given by the square root of the tension of the string divided by the mass per unit length of the string itself. The mass per unit length of a string can be calculated by taking the total mass of the string and dividing it by the total length of the string. And we can calculate the frequency of, well, the fundamental frequency if we know the mass per unit length of the string, the tension that's across that string, and the wavelength of the wave. Luckily for us, the wavelength of the fundamental frequency on a string is twice the length of the string itself. Here's what I mean. I could do some calculations here using some real values, but unfortunately my kitchen scale is not sensitive enough to be able to take those measurements. But we can still use this equation to figure out some stuff. Any wave obeys this equation. Wave speed equals the frequency of the wave multiplied by the wavelength of that wave. We sometimes use c instead of v when the wave speed we're talking about is the speed of electromagnetic waves through a vacuum. Seeing as the speed of a wave on a string is given by the square root of tension over the mass per unit length, let's put that into our equation. The wavelength of our fundamental frequency standing wave is twice the length of the string itself, so let's put that in instead of lambda. By the way, f now has the subscript 0, since it's not just any old frequency, it's the fundamental frequency. Rearranging for f0 gives us an equation that allows us to calculate the fundamental frequency if we know the tension in the string, the mass per unit length of the string, and the length of the string, as in the distance between the two ends that the string is fixed and can freely vibrate. For a guitar, this will be the distance between the nut and the bridge saddle. Now let's use this equation to investigate the guitar. Ignoring the positions of the individual bridge saddles, more about that in a different video, the length of all 6 strings are the same. If we were to use 6 identical strings across our guitar, rather than a usual set which have different string thicknesses, the fundamental frequency of each string would depend only upon the tension across the string. The fundamental frequency is proportional to the square root of the tension across the string. Here's where we run into a bit of a problem though. If we want to tune our guitar as normal, the higher the fundamental pitch of each string, the greater the tension that's needed across it. For a quick example, the high E string on a guitar is the note E4, which has the frequency 329.64 Hz. The low E string is the note E2, which has frequency 82.41 Hz. Substituting these into our equation shows that the tension on the higher pitch needs to be 16 times the tension in the lower one. With increasing tension in each string across the neck, the forces would be trying to bend it sideways. Ah! So instead, the thickness of the strings, and therefore the mass per unit length, decreases for the higher pitched strings. The fundamental frequency of a string is inversely proportional to the square root of mu. So the smaller the mass per unit length of the string, the higher the fundamental frequency of that string. As a result, the strings across our guitar neck then have a much more similar tension to each other. And this way we don't bend our guitar neck sideways or anything. Thanks for watching. I hope you found this useful, and please feel free to like, share and subscribe. And if there's any other videos you'd like to see or suggest, please put them in the comments below.